So I'm Miki Elad from the Computer Science Department here in the Technion, and I'm going to talk to you today about three topics that are connected in a very interesting way. I'm going to talk about sparsity as a way of modeling data. Then I will take it to graphs and show you how I create a model that sparsifies graph information in order to handle them. And then in a very strange turn of events, I will take this to image processing, and I will handle general purpose image processing problems. So 3 colors, yellow, blue, and green, 3 parts to this talk. Let's begin. Okay, so the first part, the yellow part, is about sparsity. And I'm interested in explaining in a very broad way why sparsity is so central and so important in modeling of data. And I'll start with, you see, by the way, this small text. Don't bother reading it. It is just for completeness of the slides. These slides can be found in my webpage, so when you download them, you will see this text, and then it might help you. So just before I start, it's always great to start with good news, and the good news today, terrific news in fact, we can process data. We are excellent in processing data. We have the skills, we have the math, we have the know-how. We can process data. You may ask, what kind of data? Well, really all sorts. Videos and all sorts of imaging, text documents, graphics, medical information, financial information, and the list goes on and on. We can process data. We can do it very efficiently. And when I say process, what do I mean by that? Well, this is a very long list of capabilities, starting from removal of noise from your data, going through interpolation, filling in missing values, extrapolation, basically prediction, compression, separation, you name it. The list is long. We should be proud of ourselves. We can do all these things. Now, here is a question. Why? Why can we do all this? Is it obvious? Is it a God-given fact that we will be able to process data? Here is, for example, a source of information, an innocent source just generating IID random numbers, long list of them. This is basically a dead end in terms of processing. You cannot do anything on it. So clearly, you cannot process any source of information. There is something unique about the data that we do process. What is it? What's so special about the data that we are able to process? And we know the answer. We know the answer. We have been through it many, many times. There are many ways to pose the answer, but the essence of it is very simple. The data we operate on is structured. Okay? You can talk about low entropy of the data. You can talk about the geometry, talking about low dimensionality in the embedding space. You can talk about manifold structure. It all comes back to this. The data we operate on is structured. What does it mean? It means that if you bring me a source of information that has n values, for me, a data is a pile of numbers. So if you bring me a signal, a data source that has n, capital N numbers, then essentially I'm telling you, no, it doesn't really contain n numbers. It has way, way less. In fact, only k degrees of freedom, where k is way smaller than n, is really encapsulating the data in your signal, in your data. And you can think of this as sort of a concentrated juice of this vector here. Moreover, I could take this vector and recreate x with the choice of a very specific function, f theta of v. So let's talk about the relationship that emerges here. Let's talk about this innocent-looking equation, x equals f theta of v. So this equation basically tells us a story. And the story goes like this. You bring me your data, a vector of length n, and I believe this is something very fundamental about models. We believe. You cannot prove the correctness of a model. You can just demonstrate it, very much like a theory in physics. You do not prove a theory in physics. You just demonstrate and align it with measurements. So I believe I could find a model that starts with a very short vector, the representation. This is how I will call it, the representation or the innovation. This is really the core information in your data. And I can recreate your x from v by some wisely chosen function, which we will talk about. Okay? Moreover, this function is typically chosen such that it has some flexibilities. This is exactly where machine learning comes into play. You will be tweaking those parameters to fit this f to your data in order to do justice to your information. Okay? Last part in this equation, this equality, don't believe in it. Nothing here is equal. Models are always wrong. We have to be aware of this when we deploy models. They are making mistakes. It doesn't mean that they are useless. It just means be careful when you are using them. And just one final comment. This is just one way of posing the structure that may exist in your signal. There are other ways. I will refer to this as the synthesis model, well, simply because it synthesizes X from the innovation. Okay? Now, so we asked, why is it that we can process signals? And we gave an answer. The answer was because they are structured. Okay? But this is only part of the truth. If you want to process signals, it's not enough to know that they are structured. You need to know how they are structured. I need to know F. I need to know theta. Only then I can go about processing this signal. Okay? So let me show you a few such examples that give you the flavor of things. Suppose I know that X comes from this model. Suppose I know everything there is to know about F and theta. Assume that I'm interested in compression. You gave me X, you want to compress it. What do I have to do? Well, I have to solve this equation, find V, and V is your compressed version of X. This is compression in the most elementary way of seeing it. Okay? This is just one option. Suppose that someone gives you Y, a set of measurements that are related to X through a linear operator M plus some random noise. Suppose I want to recover X now from the measurements that I do have. What do? Well, under the assumption that I know the model, this is posed as this optimization problem. Find X such that Mx is closest to Y, and then don't forget, X has to belong to the model. And here is a little bit of intuition about this formula here. Suppose that M is fat and short matrix, which means that when X was multiplied by M, we actually lost a lot of information. Using the measurements alone to go back to X, you are lost. You have no chance of doing it. Then comes this part which serves as some sort of regularization, reducing the true dimensionality of your unknown, therefore enabling you to come back to a proper estimation of X. This, by the way, covers sequence of applications, tomographic reconstruction, prediction, inference of all sorts, interpolation, denoising, etc. One last example. Suppose I want to separate two signals where I have the mixture of them. So someone gives me Y, which is X1 plus X2 plus noise. And I want to take this Y and break it three ways. Well, I will assume that X1 and X2 are coming from different models. Okay? And then separation is almost trivial. You have to find X1 and X2 such that their sum is closest to Y, such that every one of them belong properly to this model, to their model. Okay? And of course, this will succeed only if the models themselves do not overlap or their overlaps is controlled. Okay, so this was all very broad and very vague. Let's put things on the ground now. Let's see something very specific in order to understand what I'm talking about. This is an audio signal. This is a guitar playing, okay? And I'm going to look at n samples taken from it, a portion of n samples. And, you know, n samples like this form a point in Rn. N samples, Rn, this is one point. I'm going to slide this window and accumulate many, many points. Okay, I'm talking about overlap patches extracted from my data. I took all of them, and I get this lovely set of points, and I'm trying to figure out, in this array of vectors, every one of them is of length n, is there a structure or not, and what is it? So, you know what, one of the simplest things you can imagine, and we use it all the time, is to believe that all of them reside in one single subspace. One subspace of dimension k. Remember this f function? In our case, it will be very simple. It will be just narrow and tall matrix Q multiplying the vector V in order to get X. So basically what I'm telling you here, in this model, I believe that every one of those X's can be written as a linear combination of the k columns of Q. This is a model assumption. It might be wrong, it might make some mistakes, but this is what I assume. Okay? And in terms of the parameters theta that I have to tweak, well, this is Q. You will have to adjust Q in order to squeeze the best out of this model. We all know this model. It has many names. It was conceived many times because it is so basic. It is called PCA, it is called KLT, it is called Hotelling transform, and it has probably more names, simply because it is so simple to use, but of course, it is also a bit crude, so we can refine it. For example, if I zoom in on one of the points in this cloud and just look at it and its neighbors, and I'm talking now about neighbors in Rn, neighbors not in time, but neighbors here in this vicinity of this point, then oftentimes, for most of the sources that I presented in the first slide of the talk, for most of the sources, you could assume that locally you are behaving like a subspace of very low dimension. And the reason, by the way, is very simple. Because data tends to behave like smooth, curved manifolds. And so, locally, you can linearize the manifold, and what do you get? You get this subspace. Or let's call it an affine subspace, because it is shifted. Okay, so this can be harnessed in all sorts of ways. And one of the simplest ways, and by the way, very elegant and very effective, is what we call the union of subspaces model, which basically says, you know what? Don't assume that all of these come from single subspace. Assume that you have a group of them, like this. So basically, some sort of clustering is taking part here. You cluster the data into subgroups, and then every group gets their own private PCA. Okay? And again, the equation is very similar to what we had before. X will be Q times V plus some shift, but those Q are different from one subspace to another. You want to train the model, you have to find those Qs and Cs, and basically you got it all. This is a very commonly used model. In image processing, it is doing a great job. In speech recognition, its cousin, the GMM, the Gauss mixture model, is actually leading today in results, again, speech recognition. So apparently this works quite well. And just to illustrate how you can work with the model and why knowing a model you can process things, imagine the following. Suppose that I have X known to belong to the PCA model, and suppose that now I want to denoise Y. That means you give me a noisy version of X, and I have to clean it up. So geometrically speaking, you gave me this point Y in Rn. This red carpet is basically the space or subspace containing all the permissible signals. This is where your data should live in. Basically, what I have to do is to project, is to search for the closest point to Y on the carpet, and this will be the way of cleaning up the noise. Algebraically speaking, what I did here is to search for the closest point X to Y, such that it belongs to the model, a little bit of algebra, and it leads to whatever I've just shown you here. And I mentioned before that we can do signal processing, we can process data effectively. What did I mean by that? Well, look what happened here. By projection of this sort, most of the noise that was in Y vanished. It vanished because now I project onto k-dimensional space, only k out of n portions of the noise remain. That means that most of the noise has been wiped out. Very nice. This is the effectiveness I talked about. And just for completeness, if in the case of union of subspaces, if I have a bunch of subspaces together, what do I have to do? Well, I will have to project onto each one of them separately, and then choose the one that gave me the closest projection. Okay? So it's L time more complex, but if the model is better, why not? And all this was background in order to talk about sparsity. So let's talk about sparsity. Remember, PCA says, I believe that every one of those vectors can be described as a matrix times a short vector. The matrix is tall and narrow. Lovely. Well, now comes the sparse modeling. Again, this is the target, finding structure in those vectors. And this is how it looks. At least algebraically, matrix times vector equals your data. Looks very similar with one major difference. The matrix is fat. The matrix has even more columns than rows. So something has to be explained here, because now AI, the representation, is actually longer than your data. I'm exploding the information instead of condensing it. Then comes the restriction. AI has to be sparse. This vector here, most of its elements are zeros. And so only few of them are non-zeros. And basically those choose very specific subgroup of the columns, combine them linearly in order to generate your data. We call this matrix the dictionary. We refer to the columns as atoms. And you know what? This is some sort of chemistry interpretation of data. What I'm telling you is this. You brought me this vector of data. I think of it as a molecule. You just brought me a molecule, and I believe that it should be composed of several atoms, only few of the atoms in the periodic table. Mendeleev periodic table, in my case, these are the columns here. I have many of them, but only few of them will participate in creation of any molecule at any time. Okay? This is the model assumption. So let's talk about it a little bit more. First, in terms of dimensionality reduction. What happened here? If this vector has only k non-zeros, this is how we denote it. If it has only k locations where it is non-zero, then how much information does it carry? This vector is indeed long. It is p element long, okay? This is p, but most of them are zeros. The amount of information really held in this vector is just 2k. And if k is way, way smaller than n, you are in good shape. You are condensing, you are reducing dimensionality, as you should do. Secondly, in terms of geometry, what do we have here? Suppose that I took this data and I found k atoms that are constructing it. Suppose I've done this. Now suppose that I go to my database and I find many, many other vectors, many other data vectors that share the same atoms, that use the same atoms to construct themselves. What is common to all this group? The fact that they are using the same atoms really implies that they are coming from the same subspace. So what I'm telling you basically that every k atoms chosen here form a single subspace for which some of the signals may enjoy and benefit and be there. Okay? But how many are there? How many subspaces altogether? P choose k. Of the p columns, I have to choose k, and this is going to be a huge number. Every one of them is going to create a subspace to serve your data. Okay, so what I'm telling you is that this sparsity model is yet another way of forming union of subspaces of the kind I've shown you before. But it is very different. It is different in the sense that it has way more subspaces, and all of them emerge from the same matrix, innocent-looking matrix D. Let me give you an example of numbers. If this matrix is 200 by 400 elements, then if k equals 10, k atoms are participating in constructing any piece of data, then in terms of dimensionality reduction, the factor is 10. From 200 to 2k, which is 20, I'm decreasing the amount of information by factor 10. This is very effective. In terms of the number of subspaces, this is the number. Look at it. It's huge. Okay, and we'll come back to that. In order to use sparsity in practice, let's see what we do. Let's just revisit the problem of cleaning up a signal from noise. So again, I remind you, you have a signal X that is noisy, you want to clean it up, you basically project, which is nothing but finding X closest to Y such that it belongs to the model. In our case, this is how it looks. You have to find a K element A, a vector A of length P, which will have only K non-zeros, such that dA is closest to Y. This will give you A hat. Nobody cares about A hat, so you want to multiply by D in order to go back to your clean signal. This is a very tough problem. Why? Because in light of what I told you before, what we have to do is to project your data, Y, onto every one of those subspaces. How many are there? In our example, for example, 10 to the power 19. You will have to project onto every one of them, basically checking every possible support for A, and then choosing the one that gave you the best results. You are dead. It will take you a lifetime to finish just one such process. By the way, in image processing, we solve these problems something like 1,000,000 times in a second, so obviously something can be done. This is known to be NP-hard problem, so what we do is to approximate. There are all sorts of approximations, and there are all sorts of proofs to show that they are operating good under some conditions. Let me show you one specific approximation, which is a simple algorithm, and I have to show it to you because I will use it later on. Okay, so it's called the thresholding algorithm. Very simple algorithm. It says the following. Don't be alarmed from this equation. It says something very simple. It says this. Take Y, your corrupted data, and multiply it by some matrix. This matrix, D pseudo-inverse, is basically sort of inversion of D. We'll call it omega. This is how it looks. If D is elongated this way, omega is tall this way. So you multiply by omega your Y. You get a long vector. The length is good, but not the content. What you do now is to push this vector through this function. element-wise. Every small element simply becomes 0. Every dominant element, either negative or positive, remains. And you get a sparse vector. This is A hat. Okay? Sometimes it works great. Sometimes not so bad. So not so good. This is the approximation algorithm. And just one thing. What about the case where I feed this algorithm with a clean signal? Obviously, if I feed it with a clean signal, I don't want this signal to be damaged. Okay? So in that case, what I need to have is that omega, when it meets a clean signal, it will produce a sparse outcome to begin with. And so here is a thumb rule for the goodness of such a matrix omega. And I'm using it in a minute. Omega will be a good operator if it sparsifies signals of interest. So when it multiplies a good signal, it gives us something that is nearly sparse. Let's leave it at that. So this was a crash course on sparsity and its role in modeling data. So to summarize, if you are going to process data, that means you are going to lean on the structure that exists there, and that means using models. There are all sorts of models. Sparsity-based models are today very hot topic, very promising. They are, in fact, some sort of union of subspaces, as I've shown you. And now I'm going to take this concept and bring it to graphs. And just to give you a look ahead, graphs are not what interests us. We will take this and then bring it back to image processing. And you will see eventually how we do image processing with the development for graphs. And just before I go to the next part of the talk, I want to say something about why work on graphs and why have I chosen this topic to this event. Well, graphs are really a hot topic today in signal processing. You see it by special sessions in conferences. You see it in special issues in journals. Graphs are prominent structures of information because of the internet, because of social networks. So people are very interested, and we are too. But the true reason to show this work here is the fact that the results you are about to see from now on are all the fruits of a collaboration between myself and Idan Ram and Israel Cohen, both of them from the electrical engineering department. I remind you, I'm from the computer science department. Idan is doing his PhD in the EE. Israel Cohen and myself are serving as his advisors. And so this is really a collaboration of two departments, which is exactly what this TC is all about. So seems appropriate for this event. OK, so let's talk about graph. We are moving from the yellow part of the talk to the blue one. Good. Now, forget what I said and just open your mind to a new way of looking at data. Someone gives you a graph. It has nodes. It has edges. And the nodes are characterized by having features. Every node has a feature of length n, xi. Every node has, on top of that, a value, gi. Okay? This is my data structure. I didn't say anything about the edges, so let's say something. The edges carry the distance between the features. So for example, from here to here, this will be the distance between x5 and x12. What is the distance measure? You choose it, whatever you want. Okay? This is my data. This is the data I would like to operate on. Now, I'm going to assume an assumption here. I'm going to assume that a short edge implies close-by values. It means the following. If W of xi, xj is very small, then in most cases, not always, in most cases, the distance between the gi values, those scalar values, is also going to be small. Okay? We will see this in a minute in a different way, which maybe will make it clearer. Because there is a different way to look at this data set. And the different way is this. Someone gave you a bunch of vectors, xi's, okay? x1, x2, x3, up to xm. All of them vector of length n. Someone gave you, attached to this, a value per each. A value, gi, corresponding to the xi. This is the node, feature and value. And you know what? You can think of all this as a function, g, from Rn to R that someone just sampled m times. There is a function here, and someone just gave you coordinates and value. Coordinates and value. Okay? So this is my data set, samples from this high-dimensional function. And the assumption I told you before about small distance implying small difference between the g's is simply some sort of regularity that I assume on my function g. Regularity means I'm assuming some sort of smoothness of g. or piecewise smoothness, something that makes G reasonable and not jumpy like crazy. Okay, now here is what we are trying to do in this part of this talk. We would like, please do not be alarmed, we will talk about Wavelet. You don't have to know anything about it. The way I present it basically is self-contained. So here's what I want. I want to take the G data. This is my data. I want to take the G data, M values, and I want to model them. I want to find structure in this vector. And so I will try to come up with a transform with an operator that will sparsify them. Because we just agreed a few slides ago that sparsification is a way of getting to the structure of the data. Now, this transform will be done with the help of the x's. Those coordinates will be side information to our design. They will help in designing this operator here. Okay? So why Wavelet? Simply because in the world of harmonic analysis, the world of signal processing, image processing, wavelets are the way to sparsify regular or semi-regular functions. If you have data that is behaving regularly or nearly regularly, then Wavelet will do the sparsification which we so much want. So all I'm telling you is I want to imitate this and bring this to my data, to this data. Okay? This is my goal. So let's see what we do. Just before that, let me tell you, this is a terrific idea. Designing a wavelet for graphs is a terrific idea, and there is one major flaw in it. We are not the first to think about it. We found, when we started in 2008, that there are plenty of works suggesting already all sorts of ways to adapt wavelet to graphs. So we studied this work, and from these, we found this one especially to be very important and very central to our work. So basically, what I'm going to show you is how we stood on their shoulders in order to come up with our own solution. This is Matan Gavish, Boaz Nadler, Rafi Koifman work on how Wavelet designed for semi-supervised learning, and we take this and bring it up. So let me tell you what we did. The core idea is permutation, and it looks like this. This is your vector G. It doesn't look like something you can operate on. It doesn't show the structure in it. So what do? We will permute it. We will reorganize the elements so that it looks smooth, and then you can operate on it using traditional tools. Okay? We will use the coordinates in order to come up with the permutation that will serve well. Okay? And then at least the core idea would be, if you know how to permute, then given G, permute the vector, then do whatever you want, and when you finish this transform wavelet, process, inverse wavelet, and then when you finish, don't forget to permute back. That's it. This will be at least the core idea. But actually, we do something more complex, because wavelet is a pyramid. Wavelet is taking data and creating a pyramid of resolutions by filtering the incoming data in two ways, low frequencies, high frequencies, two branches here. And then you take the low frequencies after decimation and yet again apply low and high frequencies. So basically what we will be doing is to squeeze permutations inside every one of those layers. So in 10 levels of a pyramid, we will have 10 permutations. And of course, you'll have to invert them. And here is a bizarre way of thinking of these things. Wavelet is a transform. Wavelet is a matrix that you multiply your data with. If you think of those permutations as additional matrices coming into play, then from end to end, this is a linear operator. So I'm remaining linear, so to speak. It's not truly linear because those permutations will be depending on the data. Okay? So how do we permute? Let's start with the first of them, the one that actually meets the data as it comes. We want P0G to be as regular as possible. But I remind you, we are not going to meet good-looking Gs. We are going to meet some damaged Gs. And so the question is, what do you do with this? So what we suggest is to harness this property that I kept mentioning. X's implies closed Gs. And so this is a measure of smoothness of the G after permutation. This is what you want to get. You want to find P that will give sum of absolute local differences to be minimal in order to get something very smooth. Instead, we will solve this. We will find the permutation that gives you accumulated local distances to be minimal. What is this? This is the traveling salesman problem. So what I'm telling you is this. You will start with a set of coordinates in Rn. This will correspond to a set of values in G. Okay? And now I will go to this set and I will search for the shortest path. I will start from one point and I will search for the shortest path, which tells me go from x2 to x7 and then from x7 to x4. This will dictate reordering. So based on the ordering of the x's, I will find order of the g's. And now the g's look better. And why should they look better? Because of the assumption. Close by x's gives close by g's. Okay? And what we do is to apply a greedy algorithm to solve this problem. So the crudest way you can think of organizing the shortest path, basically finding always the next nearest neighbor. That's it. Okay, what about the rest of the permutations? So here is what we do. We take the original set of coordinates and we use them in order to find the shortest path, and this gives us a permutation. We apply the permutation on the x's themselves, and we fit them into the wavelet itself. So basically, we do not just filter G, we filter the coordinates themselves. So here we get a new set of coordinates, filtered and downsampled. Those are used in order to redesign a second permutation and so on. So what I'm telling you is the process will actually be applied not only on the G values, but also on the coordinates X values. Okay, so we have all the permutations. We call this the generalized tree-based wavelet transform. It works lovely. We designed several versions of them. At this point, you might expect me to show you some results on graphs. And we do have such results, I'm happy to say. But I'm not going to show it because now I move to something entirely different. I move to image processing, signal processing and image processing. And I will tie this to something that we did before but did it wrong. So just to summarize, given a graph, if you want to model it, you can apply wavelet but with permutation the way we suggest, and this will sparsify your graph and therefore lead to the ability to process it in all sorts of ways. By the way, processing graph, what I mean by that, for example, cleaning the G's from noise, filling in missing values, finding outliers, and all sorts of these applications. So let's talk about images. Okay, so remember this signal, the audio signal, the guitar playing? Remember what we did? We took a portion of n samples, and this was a point in Rn. Well, this is actually a vector, okay? So let's look at these as just a bunch of vectors. We slide this window and accumulate many, many vectors. What have we done so far? What have we done in the first part of the talk? We invested a lot of time in finding the structure that exists within every one of those columns. Remember, for example, in the PCA, I took this vector of length n, and I told you how I can reduce it to a length k. This is lovely. But what about the connection between the columns? Who told you that I'm interested in modeling small portions of the signal? What I want to do is to model the entire thing. So I didn't do good job in squeezing really the structure of the signal. Instead, I satisfied with seeing the structure that exists in small portions. So this is exactly where graphs will come to play. Let me give you an example to illustrate what I'm talking about. Imagine a situation where these three columns are just the same, exactly the same. If I work with PCA, for example, then every one of them will be reduced to k dimensions, but holding the very same k values. So the fact that these three, and perhaps others, have the same values, it is a redundancy that should be exploited. At the moment, I'm not doing anything about it. So let's do something about it. And what I'll do about it is to bring graphs. And the idea is very simple. Forget about the origin of this matrix. Forget that there is audio behind the scene. Just think of these columns as if they are features of a graph, and just apply the transform that I've just shown you. This is the idea. So any signal, even uniformly sampled, can be turned into a graph, and from there you can use the tool that we have developed. We will do this, but for images, which is almost the same. So here's what we will do. This is an image. We will break patches out of it. I'm talking about all the possible patches with overlaps. Every patch is of size square root of n by square root of n. That means a vector of length n. And I will create this array of vectors. Okay, so I have now the x's. What about the g's? Well, the center pixel in every one of those patches will be the g of that x. So basically, it is the center line in this array. Now I have a complete structure for which I can apply my graph transform. I forget that this array of vectors is coming from an image. I don't care anymore. And I'm just processing it as a graph. And let's see what happens. So I remind you, what do we have in terms of a graph here? We have an image that when I order all its pixels in one long vector, column by column, for example, this will form my G. And the same pixels taken in a different structure will create many, many patches. Okay? I design a transform that can take all these patches and I transform the patches themselves and get many, many coefficients. And if I forget conveniently what happens from start to end and just remember the beginning and the end, then I can think of this as a one big, horrible size omega, an operator that goes and works on the image G in order to generate a very sparse vector at the output. This is my transform. This is a new model for images. It is a way of modeling images. Let's apply it. We can apply it. Now, I can think of this as a linear operator, but actually, this is wrong. It's not linear. This is not a linear operator, despite the fact that I show it as a matrix. Why? Because here, in the hidden part, I actually used the pixels themselves in order to permute things. So it's highly nonlinear. I just forget about it. Secondly, this is a matrix that is adapted to this image and this image only. It is good only for this image because all those permutations have to do with the relation between the patches. So this is the transform dependent on this image alone. Okay? So, yes, definitely skip. So let's clean up an image just to see how it works. Remember, if you give me a noisy image, I can clean it up. And I can do it using this crude algorithm that I mentioned before. I told you about it. This is the thresholding algorithm. I have omega. I have D. So I can do it. And basically, it says this. Take the image, apply the transform, the one that I've shown you, threshold small values, just every small value, negative or positive, just null to 0. Do the inverse transform, and you will be looking at a good-looking image, hopefully. Okay? Now, this is exactly what we did. But just before I show you result, small comment. We have to be careful here. We are about to make a mistake of the same kind we did before. Before, we modeled the columns and forgot about the connection between the columns. By going to that wavelet that I've just shown you, we will be handling the columns, in between columns connection well, but forgetting about the within columns structure. So you want to do both, and we did both, and these are the results. Input, noisy, and denoised. And the results in a table are very impressive. We get results with this algorithm, which has what? A wavelet for graphs and a thresholding algorithm, that's it. And it gives us results that are nearly as good, or I would say competitive with the best known method today. And this is with a simple algorithm, basically. Okay? So quite impressive results, and of course, giving us a lot of hope for the future. So what next? Now that you have a sparsifying transform, you can take it as a general model and do all the activity in image processing. This is one option, which I'm going to skip. The second option is very interesting, and it is something very intuitive, and I hope you will like it. And so let's skip. The second option basically says, you know what? Look carefully what you did. Forget about all the layers of information that you threw. Just keep the core idea. And what is the core idea? Permutation. Let's take the permutation and see what we can do with it. So here is a new way of practicing image processing. Okay? It goes like this. You give me an image. I will break it into many, many patches. I'm talking about all the patches, including overlaps. Okay? So the number of patches is, roughly speaking, as the number of pixels. I will take all those patches and organize this long sausage of patches organized next to each other. And the unique thing about this sausage is that it was created by solving or approximating the traveling salesman problem. So basically, I'm trying to figure out a sequence, an ordering, let's say, of the patches that will give me the smoothest and the shortest path from the beginning patch to the end. Okay? What's so special about this? Now, if I take the center pixel in all those patches, the center pixel, what is it? It will create 1D function that contains all the original pixels in the image. Why? Because every patch is a center of a specific pixel. So taking the center pixel here is just like taking all the pixels in the image in a new order, and a new order that the permutation induced. This new order is amazing. In what sense? It is creating an order where the signal is very smooth, 1D and very smooth, for which you can apply simple algorithms and benefit. So here is how it looks. First, I'm telling you, if you take the center pixel, it's going to create a very smooth function. This is a graph that tries to show it. Let's see if it plays. What you see here, this is a very long vector. I cannot show it entirely because then you will see nothing. So instead, what I show is a window running over the signal, running over the 1D signal. What you see in red is the ordered pixels based on the patch ordering. What you see in blue is the raster scan image, the way you would be ordering pixels in a natural way in images. The green one is a fractal structure that goes in the image and trying to preserve neighborhoods, and therefore it should be smooth. Now, which of the three is the smoothest? I argue that it will be the red. The red is much more relaxed in changing its levels. So the idea is this ordering actually gives us a very smooth signal. Moreover, if you give me a noisy image or corrupted image and I do this ordering, I'm quite robust to the degradations, and I will get a good ordering nevertheless. And here is what I'll do with it, and this is on an intuitive basis. Someone gives you a noisy image. This is the pixels line by line, for example. White corresponds to true value, black corresponds to the given value. You want to go from the black values to the white ones. How do you do it? It's very hard to see anything to do. It looks so complicated. So what do you do instead? You take this image, break it into patches, order the patches. Ordering the patches induces reordering of the pixels, and you get now a reordering of the pixels. Now, I told you, if I reorder the pixels, I'm expecting something smooth. If it is not smooth, it is because of the noise. So I will just smooth it out, run a low-pass filter, dumb low-pass filter, and that's a true result. So apparently you can clean up an image and get nearly state-of-the-art results with something so simple as reordering of the pixels. That's it. Another example. Someone gives you this, an image with 80% missing pixels. Black corresponds to a missing pixel, white corresponds to a known one. So you want basically to fill in the missing values. How do you do it? Well, it's very hard to guess what will this be based on its neighbors. Very hard. And you can do it, but it doesn't work that great. Well, permute. Order the patches, reorder the patches, and basically reorder the pixels. Now you get this line, and you know that the signal should be smooth. So interpolate very simply. Those are the missing values. Go back and position them, and this is a true result. So ordering does work, and ordering was the essence of the idea that we did before. And what you see here are the results, 80% missing pixels. This is bicubic interpolation. This is DCT and OMP, leading method today. And this is what we got one round. Think about it. When I start the process of ordering the patches with 80% missing pixels, how can I order things? Most patches are just empty. So what I have to do is to fill in with something, order, get a solution, and then reorder, etc. So several rounds will help. And what you get here are the results after 3 rounds. And the results are really, really better, much, much better than state-of-the-art. OK, time to finish. So I told you the slides can be found in my webpage. What we talked about is modeling as a way of exposing structure in data in order to process it. We talked about sparsity-based models and how effective they are. We then took them to graphs, and from there, in an awkward way, we brought them back to image processing, and we did image processing with this. Plenty of ideas come next in a very natural way. Thank you very much for your time, and thank you very much for the organizers for inviting me. That's it. I finished.